Okay, so it's short, lecture number 12. We will talk today about stereo cameras, about disparity estimation and depth estimation, and about dense matching for estimating disparity and depth. We will talk also about regularization and smoothness for disparity estimation, why it is important and how to do that. And we will review some deep learning approaches for disparity estimation. And finally, we will talk about image rectification for using disparity algorithm for general two images. Okay, so the motivation for today's lecture is to get dense reconstruction. So the goal is that if we have two camera matrices, we want to have the depth for every pixel in the image. And that actually requires every point in the image to be matched, not like what we had before. So the setup is that we have two cameras for today's lecture, P1 and P2. And we know that if we have a correspondence, X and X bar from two images, then we can look for capital X such that capital X is projected to X using P1, and it is projected, and using P2, it is projected to X bar. So that's a triangulation problem, and we saw a linear solution in lecture 3 and other solutions in later lectures. But we want to have dense matching pixels, not like what we had before. And before we only considered feature point correspondences. So just to put this in the global context of this course, before we had sparse point matches from SIFT, for example, and we were able to get the two cameras and to have a sparse reconstruction as a result. But today, what we want to achieve is to have a dense reconstruction, which require dense point matches. And for the global context of the course, in the last 2 or 3 lectures, we talked about structure for motion, where we have a set of images where we want to produce cameras and sparse reconstruction. Next week, we will talk how to get set of images and sparse points and cameras, and to achieve dense reconstruction. So that we'll talk about multi-view stereo next week. So for today, when we're talking about two cameras, we will start with rectified stereo cameras, where in this case, we have a simple set of two cameras that we will define. So the assumption is that we have two cameras where both of them look to exact same direction with the same calibration. And camera 2 is just an offset of camera 1 by distance of b in the x direction. So that's rectified stereo camera. That's the definition. And now we want to see how corresponding point resulted from the projection of a 3D point, how they look like. So we have X, capital X, that we project to camera left and camera right, and we want to look at these corresponding points. So let's look the equations. So we have the calibration in this case, and we have a PL and PR as we defined, and we have a 3D point capital X defined in homogeneous coordinates. And then first, let's multiply capital X by PL. So we have a PL here, and we multiply it by X, Y, Z. So we first multiply this part by X, Y, Z, 1. So we have identity multiplied by X, Y, Z minus 0 times 1. So we get X, Y, Z. And then we multiply the calibration matrix with X, Y, Z, and we get this following vector. So to get image coordinate, we need to divide by third coordinate of this vector. Then we get the following two coordinates, the x coordinate and the y coordinate for XL. Similarly, for the right point, we multiply PR by capital X, and we get this camera matrix representation, and here we use I multiplied by x, y, z minus plus minus b 0, 0. So we just have x minus b, y, z. And then after multiplying again with the calibration matrix, we get this expression, and we divide by the third coordinate, and we get these two coordinates. Now, first thing to note is that xl and xr have the same y coordinate. Okay, so that actually means that corresponding epipolar lines that we talked before will always be the same line that is parallel to the x-axis. So that will be corresponding epipolar lines, because corresponding points will always have the same y coordinate. And another thing that we can do, we can define the following value, which is called disparity. For conveniency, let's show XL on the right image, and then the disparity is just XL minus XR in the X coordinate. That would be the disparity value. Okay, so now let's see what is this disparity. Let's calculate it. So we know XL and XR in the first coordinate, and we just subtract these two values. So first you can see that x0 is cancelled because we have x0 minus x0, and fx capital X is cancelled also, and then sy is also cancelled, and we get just b fx divided by z. Okay, so what does it mean? It means that b and fx are just values with respect to the cameras that we have. They're constant. B is the distance between the cameras. Fx is calibration information for the cameras, the focal length in the x coordinates. But what we see is that we have this inverse relation with respect to z. If z is larger, we will have a lower or smaller disparity. And if z is smaller, we expect to have a larger disparity. Okay, so let's see it in this illustration. If we get lower z, closer point, we will have a larger disparity, and if z is larger, we will have smaller disparity. Okay, so large disparity, small disparity. So we have this relation. So we know to calculate the disparity from when we know z and the camera calibration. So in the same way, we can calculate z from disparity. So if we know the disparity, we know the depth. Okay, so let's see some real example. Here you can see the right image and the left image taken from the Kitty dataset of driving cars. And first note that a line that is parallel to the x-axis is corresponding epipolar line. And also, we see that for small depth, we have large disparity. And for large depth, we have small disparity. And we can also plot the depth as a function of disparity, where we assume a b of x equals 1. And you can see that for larger disparity, we get lower depth. Okay, so any questions about the definition of rectified stereo cameras? Okay. Okay, so since our goal is to find disparities for calculating depth, then it is convenient to, and we want to do that for every pixel, then it is convenient to display an image of disparities, which is called disparity map. So for every pixel in the left image, we find its disparity to the right image. So for example, here we have a correspondence for left pixel 150, 200, and in the right image we have 100, 200. So the disparity is of 50 pixels, and we mark it as red in the disparity map to denote 50 pixel disparity. And if the disparity is of only 30 pixels for a point that is more distant, then we have a disparity of 30 pixels, which we marked in blue, which means lower. Okay, so that's just a way to display the disparity map. So our task is basically for each pixel in the left image to find corresponding pixel in the right image from different disparities. Each disparity define a corresponding point in the right image, and what we need to do is to find the disparity that gives us the corresponding pixel. So we need some metric to find corresponding pixels according to disparities. So until now we talked about feature points like SIFT, but in this case we don't need we don't need key points. We need measurements everywhere, and also we assume that the cameras are known, so we don't need this scale invariance properties or rotation invariance properties of SIFT. One possible way is to use SAD, which means sum of absolute differences of two patches. So we have two patches and we need to calculate the distance between them. So we just go over every pixel in the two patches and find their distance or the absolute difference and sum over the absolute differences of all the pixels in the two patches. So that's a very simple metric. So basically, if we get low distance between patches, we say that they are similar. But if we get a high distance, we say that they are not similar, and we will not choose the disparity for patches with high SAD. Okay, so let's see what SAD gives us. So here you can see the input image, and that's the ground truth disparity. Here it is denoted with grayscale values, but it's the same idea. Brighter means larger. So let's see the disparity results where we use patches of size 5 by 5.
The disparity here,
yes,
like we only see a image from one camera. So when you say disparity, you mean that there is another one, or like
yes.
what's different from saying like here's the depth of each point?
So we see that depth and disparities have a direct relation. We have two images. Here I only show one of them, but we have two images. That's the left image and that's the right image. See, it's not the same image you see here on the edges. What we show here is the disparity map, not the depth map, because closer is larger. So it's a disparity, not the depth. But you could show the depth as well. And then we just need qualitatively want to evaluate the result disparity computation, which is compared to the ground truth. That's what we show here.
Yoni?
Yes.
In the formal slide, previous slide, you have the formula I minus Y, right? When I is a patch.
Yes.
So in this slide, I need what patch do you compare all the image?
So for each pixel in the left image, I take a patch around this pixel of, for example, 5 by 5. And then I want to find the corresponding patch in the right image.
So you need to slide on over the image on the second image and find the corresponding, right?
Yes.
And then you, for each, what I'm saying that, so if you go to the next slide, So this is only talking about the first patch and the first image?
No, for each pixel, I have one patch in the left image, and then I go over all the pixels in the right image.
And you sum all the patches.
I just take the, I calculate SAD for every, so I calculate for this pixel, for example, I calculate the SAD when I compare it to this pixel and when I compare it to this pixel. And then I take the minimal value, and then I take argmin for disparity that give me the minimal SAD. That's what I will put here in this pixel. That's the value that I want to put here.
So you go over the entire row of patches and you select the one who is minimum.
Yes, the disparity that gives us the minimal cost. Each disparity corresponds to 2 pixels that I want to compare, 2 patches that I want to compare. If I have disparity 0, for example, I might have this patch and then I'll get larger error, but for a larger disparity of 10, I will get this, I will get lower score, so I'll choose 10 and not 0. Okay?
I also didn't understand because in the same patch there are pixels with high disparity and the other pixels with low disparity, right?
Yes, but yes, that's true. But here you see a huge patch. Usually, if you use small patch, then you expect to have more or less the same disparity, right? So that's actually the reason for what you see here. For large patches, you get less noise, but less details because what you say. If I take 2 large patch, then in the same patch I have different disparities, then I'll not get a sharp result, but I'll get less noisy results. Okay.
But in each patch, what exactly like you reduce like per pixel, but what's the value that we are reducing?
And okay, each disparity that I'm looking for this pixel correspond to patch in the right image. Okay, do you see this? Disparity 0 will give me this patch, disparity 10 will give me this patch. Now I want to choose the best disparity for this pixel. The way I do it is by comparing patch around the pixel and taking the patch that give me the lowest disparity.
So how
the lower error. I take the disparity that give me lower error when comparing patches.
What's the difference between what you are just saying and just looking for correspondences along the y-axis, let's say?
It's the same, but in this case, I want to search for the correspondence. I don't have some set of candidate correspondences like before. I really want to search for the correspondence for every pixel.
Thanks.
And I do it by going over disparities.
Yoni, one more question in the next slide, if we can go. Okay, so this is you're showing the SAD results. So it's the minimum of the
argmin, not the minimum.
Again?
It's the argmin. It's not the minimum value, it's the disparity that give you the minimal SAD.
Okay, so this is follow my question is, if it's the argmin and I have 2 pixels with the same SAD, okay? How do I choose which of them is my disparity?
Yeah, so that we will see next, okay? That's a very important topic that we will discuss a lot today. Okay, usually it's not so defined, but let's continue. So another metric is called normalized cross correlation to compare patches. So if I1 and I2 are again the gray levels of 2 patches, from each pixel we reduce the average patch value, and then divide by the standard deviation of the patch. And then we just use dot products between the normalized patches to get their similarity in this case. So I1 bar and I12 are the mean values of each patch, and sigma I1, sigma I2 are the standard deviations of the patches. And the importance of this metric is that it's sometimes invariant to translation and rescaling of gray values. So it's invariant to translation and rescaling of gray values, which is sometimes handling different lighting effects. Okay, so usually it's better than SAD for handling lighting effects between two images and give a better correspondences. That's a normalized cross-correlation. But notice that NCC is similarity measure, so higher NCCs means higher similarity and lower SAD means higher similarity. So SAD is a distance measure, where normalized cross-correlation is a similarity measure. So in this case, you can see normalized cross-correlation computation. You see this pixel in the left image and the corresponding, going over the people line in the second image. For each point, we mark the normalized cross-correlation. And you can see some peaks here that are marked here. Okay, so there are several peaks here, but the peak with the larger NCC is actually the correct correspondence set. But as Michael said, sometimes it's not so strict to choose the right correspondence, especially when there are repetitive structure in the scene or in the image. Okay, so another way to match points is to learn how to match points. So in 2015, Spontaro and LeCun suggested to train a neural network to classify whether two patches are corresponding patches or not. So this network gets the two patches and outputs if they are the same two patches or if they are different, for example, in this case. So it's just a binary classification network. And we will see next the result comparing to classical metrics. Okay, so let's try to add some notations here. So basically what we're trying to do in what we discussed until now is called the naive approach. And we will see soon why it's called naive. But basically what we're trying to do is we define a set of disparities, K disparities, and we want to find the disparity for each pixel that give me the minimal cost. So UI DI is the cost for assigning a disparity DI to pixel I. Okay, and I just want to select the disparity that give me the minimal cost. So for example, here, D1 will give me large cost, D2 will give me large cost, D3 also, but D4 will give me the lowest cost, so I'll choose the disparity D4 that give me the minimal cost. So that's called the naive approach, and in the same way, we can define it as a problem of finding the disparity for n pixels together that minimize the summation of all the cost values for all the pixels. Since the pixels are independent for this computation, we can just write it in this way. We will see later why we wanted to write it in this way, but we can think about it as finding n disparities for n pixels. N is the number of pixels in the entire image, where for each pixel, we want to find the correct disparity. Okay, so a problem that we already mentioned is that
you might consider that neighbors pixels might have similar disparity, right?
Yes, so that's what we will see very soon. Okay, so as we already discussed a little bit, sometimes we have similar metric for different disparities. Okay, so for example, in this region, we will get pretty much the same SAD, and we will not know how to choose the right disparity. So, and you can see this problem in the disparity mode. This area has larger error compared to the ground truth. And while other areas are more accurate when you have a texture, this homogeneous region is more problematic for this approach. So as you said, the way to address this is to apply some smoothness and to assume that nearby windows have similar depths. So for that, we add to the original data term, UIDI, a smoothness term denoted by psi ij, where again, UIDI is a cost for assigning disparity di to pixel I, and psi ij, dij is the cost for assigning disparity di to pixel I and disparity dj to its neighbor pixel j. And we want to encourage di and dj to be close, and that will give us a smooth solution. Okay, so that's what we want to have. Okay, so for example, for neighboring pixel I and j, if the disparities will be very different, we will have high smoothness cost. And if they are the same, we will have low cost or actually zero cost if we have the same disparity for two neighboring pixels. So that's just the smoothness term. It does not consider patch similarity, just the similarity between the disparities of neighboring pixels. And how to choose such a function psi? Usually we want to choose a symmetric metric such that psi ij alpha beta equals psi ij beta alpha, and also that psi ij alpha alpha will be 0. That's what we would like to choose, and an example is just the absolute difference between alpha and beta. That's one choice, but usually a better choice would be to bound this metric with a threshold tau to allow some discontinuities that are required for object boundaries. We don't want the result to be too smooth, so we want to bound this this error in order to allow such discontinuities in the disparity estimation map. Okay, so we have this objective, and we want to label n pixels, where for each pixel we have k possible disparities. What?
A question regarding the image we just saw. Like before we rolling, like what stop you from taking the disparity of two patches that look the same, like those on the wood there, to just like be disparity 0?
So it depends on what disparity 0 give you. Like if disparity 0 give you a point in this area, then you can choose. Then you don't know if you want to choose disparity 0, 1, or 2 if you don't consider smoothness with neighbors. The smoothness solution will prevent you to choose such a disparity, because
you try to minimize it, right? So you're trying to minimize it, and so what? No, why not taking just 0?
No, I don't. Okay, I minimize the cost for matching pixel according to the disparity. UIDI is cost for patch correspondences. I cannot just put 0 here. I can put disparity 0 and get a cost that give you corresponding pixel, and then I'll see the error. But this term will not be the disparity. It will be that the cost that defined by the disparity. So I cannot just put it to be 0 easily, unless I find a patch that's really similar to my left patch.
Thanks.
Okay. So I need to label n pixels where each pixel has k possibilities. So how many possibilities do I have in total? Can someone answer? I have n pixels, each one has k possibilities. So it's a discrete problem actually. How many options do I have?
Choose k, no?
No, it's k.
K to the power of n.
K to the n.
Yes, k to the power of n, right. And so if I want to go over all possibilities and calculate the error, I can do that, but it will take me a lot of time. For example, if I have like a VGA image and with 80 possible disparities, then I have this huge number of possibilities, so I cannot really do that. So it's actually an NP-hard problem to solve this objective. And we will see there are some approximations for solving this problem. One way is to use graph cut that we'll see in the next slides, and another way is to use belief propagation that consider the problem as a marker of a random field. So today we'll talk a bit about graph cut. You already talked about it, some of you talked about it in the computer vision course of Weizmann, but we will go over it again. So for using graph cut, we need to define flow networks briefly. So a flow network is a directed graph with set of vertices. So we have n regular vertices and 2 spatial vertices, S and T. And we have a set of edges between vertices. And S and T are spatial nodes because it has only outgoing edges and T has only ingoing edges. And we have a capacity function that sets for each edge its capacity, which is the positive value. And a cut is a partition of V into 2 disjoint sets such that S is in V1 and T is in V2. For a cut, we can find its cut value by summing the capacities for edges that cross the cut from a point for a node in S1 to a node in S2. So, and it's important to say that it is possible to find minimal cut in polynomial time complexity. So that's a very brief overview of flow networks, which I believe all of you are very familiar with. Okay, so let's see an example. If I have the following cut defined by V1 and V2, what would be the cut value in this case?
CSI plus CIJ plus CJI plus CJT.
I think that I heard correctly. Yes, I think that you're right. CJ.
No, I included also CIJ. Shouldn't
no,
it be
yes.
also?
No, it's not, because you need only, it's a directed graph, so you only consider edges from S1 to S2 and not the vice versa, from V1 to V2. Okay, that's the definition of the cut. Okay, so in this case, you'll have the following cut value. What would be the cut value in this case?
CSI plus CSJ.
right? So I denote by red the edges that go through the cut, and in this case, it will be CIT and CJT. Okay, cool. So now let's go to our problem. And now think about the case, very simple case of two possible disparities and two nodes. So we have pixel I and pixel j, which are neighbors, and we want to assign disparities from D1, D2. Okay, so the way to address, to find the best solution is to define the following flow network with the following capacities. For the edge from S to I use UID1, from the edge from S to J, UJD1, and UJD2 for this edge, and UID2 for this edge, and I have the smoothness terms for edges between I and J. Okay, so let's see what happens. If I get this cut, then I know that the minimal solution is UID1 plus UJD1. So what would be the assignment if that's the case? If this is a minimal cut, what should I assign to DI and DJ?
Apparently D1 and D1 also.
Sorry?
Both should be assigned D1?
Yes, exactly, correct.
Could you explain again the connection between like the cut and the
Sorry, I don't hear you well. Can you?
Could you explain the assignment, the connection between the disparity values and the minimal cut in the graph?
Yeah, so I just define, the idea is to define capacities such that all cuts that I can get correspond to an assignment. And the cut values, each cut value that I can get correspond to one assignment. And then since I can easily get the minimal cut in polynomial time, then I actually get easily solution to the assignment problem. That's the idea. So so I just chose the solution, and then I want to see if this solution is correct. So first I want to see that for each cut I get a valid solution, a valid assignment, a cost, like energy, that correspond to a valid assignment, which is a valid possible output of this function. So here I can have only 4 assignments, right? I can use D1, D1 for both of them, D2, D2, D1, D2, or D2, D1. So I just want to see that I can get all possibilities, and then I'll know how that finding the flow will give me the lowest energy and the best assignment.
In the previous example, we have D1 till D8.
What?
In the previous example, we have D1 till D8.
D8?
Yes, because you said you have K equal to 8.
I said 80, but yes. So here I consider that K equals 2. And we will see next how to work with larger K. Okay? Okay, so if I get this cut, then that's a cut value. So I'll assign D1, D1. If that's the cut that I get, so I got UI D2, UJ D2, then I assign D2, D2. What happened in this cut? What would be my assignment?
D1, D2?
Yes, and in this case?
D2, D1.
Exactly.
Could you say why, explain again why we're considering only some of the edges between nodes I and J? So those edges which have capacity Vij, like D2, D1 and D1, D2. Can you explain again why are you highlighting only one of them in each case?
Because the definition of cut, we have two sets. One of them is with the source, and one of them is the target. And the definition of the cut is to sum only edges that goes from the set with the source to the set with the target. That's the definition of the cut, and that's what the polynomial algorithm will give me.
Thank you.
Okay.
It's not because phi ij is equal to phi ji?
No. In this case, I define it for every ij. And by the way, in this case, both capacities are the same because we use a symmetric metric, but it's just defined this way for consistency. But it doesn't really matter, actually. Okay, let's not put too much. It's very trivial. Let's continue. I think that it will be clear. Okay, so until now we saw that for 2 pixels and 2 possible disparities, I can find a easily solution with the flow network. But what happens if I have n pixels, not just 2 pixels? So each pixel has 2 possibilities. So I still have a lot of total possibilities, right? 2 to the power of n. So it's still very large. But with flow network, I can solve this and find the global minimum in polynomial running time. So we will see it next. So the idea is, like in the case of 2 pixels, I connect, oh, I don't see it. Okay, I connect, what?
We see UI, and U1, UID2.
Sorry.
Okay.
What?
No, we see everything on slide, I think, so it's okay.
Okay, yes, it's just my video occluded this information. Okay, so I connect S to every node. Here I have 20 pixels denoted from 1 to 20. So I connect the source to every pixel, and the capacity will be UID1. And I also connect every node to the target, where the capacity will be UID2 for the red edges. And also I again have a psi ij from neighboring pixels in the 2 directions. Like
what is D1 and D2?
Are the 2 disparities that I consider. I want to assign for each pixel either D1 or D2.
So it means that we have to repeat this procedure with each time with 2 different disparities?
No, we'll see next how to handle a general set of disparities, but now think about a case that I only consider 2 disparities. That's my problem. It's not realistic, but that's the problem that I present now. Okay?
Thanks.
By the way, it's realistic to other applications in computer vision, like binary segmentation. Okay, but let's not go into this application. So it could be interesting in some applications. For the disparity estimation, I agree with you that it's not realistic, but you can use this to find a general solution, as we will see next. But now we have 2 disparities. We have 20 pixels, and we want to solve the problem. This is a problem with exponential number of possibilities that we won't go to over all the possibilities. And now we see how to solve it in polynomial time. So like before, we have these blue capacities and red capacities, and the cyan capacities between neighborings. And then, for example, if V1 is with 12, 7, and 2, then I mark here the edges of the cut. And then if we look at the cut value, we see that we actually got, okay, that could be the minimal cut. We get a valid assignment that shows us to label 2, 7, and 12 with D2. Okay, these 2 nodes use the capacity of D2, and all the other nodes, all the other pixels are labeled with D1. And we got the valid neighboring psi values for not using a smooth solution in these connections, for changing from D1 to D2. So we actually get an assignment using flow network, which is very important result because we solve a very hard problem in polynomial time. That's the point of this algorithm, actually.
Yeah.
Yes?
You said that in a sense it is an approximate way to solve this problem. Why? I mean, in the case of the k equals 2, isn't it the exact global minimum?
Yes. Okay, so I say that for general k, it's approximation. For 2 pixels, it is an exact solution.
It is an exact.
Yes.
So, and we're gonna talk about generalizing it to larger case.
Yes, the next slide.
But another thing is that we assume here that like being a neighbor means that to differ in 1 pixel, right?
Okay.
So my question is whether this assumption is reasonable.
I mean, here you have only 2 possibilities, so you only have one neighboring, like you can either have the same value or have a different disparity value. So, but in general, you can choose different metric. Okay, so let's go to the general solution to an algorithm called alpha expansion, suggested by Boykov et al. So the idea is we want to solve the complete solution. So we saw that we have a global minimum for 2 classes, for 2 disparities, but here we want to label n pixels. Each pixel has k possibilities. So the idea is to break down the problem into a series of binary problems and to solve them sequentially. Okay, and where each time we choose some alpha in the set of the disparities, and we let all the pixels together to either change to alpha or keep the original disparity. Okay, so we actually can find in each step a global solution, a global minima for the decision if all the pixels want to change to alpha or not change to alpha or keep what they have. And that will give us a very efficient solution. It's still an approximation, but it works very well. Okay, so we know, so again, the idea is that we know how to solve binary problems and we use it to solve non-binary problem iteratively. So let's see how this is done. So consider again neighboring pixels. If originally they both were labeled as alpha, I don't want them to change because now I'm in iteration for suggesting pixels to change to alpha. So what would be the cut for this graph, the minimal cut? There is only one minimal cut in this case. Can you see this?
UI alpha, UJ alpha.
Yes, correct. Other cut will give me infinity cost, which I don't want. Okay, so that's the solution in this case. Case 2 is that the I and J has different disparities currently. So I has alpha disparity and J has a beta disparity. So we only want to allow J to change from beta to alpha or keep it beta. So we build the following graph, and then if I get this cut, it means that I want to change DJ to be alpha. And if I get this cut, it means that I want to keep the original labeling for J. In the third case, both I and J have has the same disparity, which is not alpha. So again, I want to allow them to change to alpha. So pixel I can change to alpha or keep beta, and also for the same for pixel J, and I will get all possibilities with the 4 different cuts. Okay, you can, I don't want to spend too much time, and you can go over it later, but it's very similar to what we had before. And the 4th case, which is more complicated, in this case, I and J has different disparities, which are different than alpha. And I want to allow both of them to change to alpha. So if I have this cut, I will change both of them to alpha. In this cut, I'll only change J to alpha. In this cut, I'll only change I to be alpha. And in this cut, I'll keep both of them to be as they were before this iteration. Okay, notice that there are more cuts here, but they will not be selected because they involve infinity cost. You see the infinity edge, red edge. And another important thing is that we don't want this cut to be selected because it gives us a non-reasonable cost value, ui beta, uj gamma, and smoothness between beta and alpha and gamma, which this is not a valid cost that we can really get. So we want to, if we require that psi beta alpha plus psi alpha gamma is larger or equal to psi beta gamma, then I will always be able to choose this cut instead, which is valid, because it will give me a lower or equal cut value. And just to say that an example for such a psi is the absolute difference between x and y, which gives us this attribute using the triangle inequality. Okay, so it's just something that we require from our psi. Okay, so in general, I will not show it for entire image, but for 5 pixels, for example, if we have alpha, alpha, beta, beta, gamma, for these 5 pixels, so we want to allow in the next iteration to C, D, and E to either change to alpha or keep their current value. I built this graph, which is just a concatenation of what we had before for different cases. We actually handled all the cases, so we can find globally a solution according to the cut. So if we get this cut, I will keep the original labels and won't change them. If I get this cut, I will change D and E to alpha, and in this case, I will change E to alpha and and also C to alpha. But you can look on it later. You look at it later if you have questions. Let me know. But it's just a generalization to what we had before for more pixels. So we can just apply it on images as well. And let's go over the algorithm. We start with arbitrary labels.
You apply this to all pixels in a one epipolar line or in all the images?
No, no, like every pixel in the left image. The neighboring is defined for neighbor. You can use any neighboring that you want between pair of pixels. It will work. Okay, like we showed in the binary example, you can generalize once you handle pair of pixels, you can generalize it to n pixels. It can be on with any neighboring definition. Okay, I want to go to break, so let's just sum up the alpha expansion algorithm. We start with arbitrary labeling for n pixel. We set success to be 0, and then we go over different labels. We let all the pixel in one iteration to either change to alpha or not change to alpha. And if we were able to reduce the total energy, we say that we got a success. So we go over different alphas, and once we finish, we check. If we got a success, it means that this iteration did something. Then we go to step 2 and start over. And otherwise, we return the labeling that we got. Okay, so this is very efficient because, again, globally, we change all the pixels together. We allow all the pixels together to change to alpha to get a global decision for all of them together. So this algorithm is not guaranteed to converge to the overall global minima. So it's just an approximation, but it can be proven that the result is within a factor of 2 of the global minimum, and it is often behaves much better. So it was a very useful algorithm before deep learning time. Okay, so let's see the result. If we use smoothness, we indeed solve this issue that we had before for the homogeneous regions. So let's go to a break of 6 minutes until.
Can I have just one question?
Yes, but I'll stop the.
Okay.
Let's go to break. So I'll stop the record. I'll pause the recording.
Pause. Yes, please pause.
Pause the recording now. Okay, so let's continue. It's recording, right? Okay. Yes. Okay. So we saw a way to calculate the smoothness to constrain homogeneous regions. So one thing that is important to talk about in the context of disparity estimation is the cost volume. And the idea is that we define, before we call it U, the cost for assigning a disparity, some disparity to pixel XY. Okay, so for each pixel, we have different costs for different disparity values that we consider. And the naive approach, or what is called the winner takes it all selection, will take the disparity with just the minimal cost without any smoothness constraints. And this different matching cost can be represented in a volumetric way, where the volume has a dimension of image height, image width, where for each pixel, we have k values for the different disparities that we consider. So that's another dimension of this volume. So this volume gets x coordinate, y coordinate, and possible disparity, and gives us the cost or the data term. And then we can use this volume to select winner takes it all selection, which will just give us the naive approach. In 2005, Hirschmuller suggested the semi-global block matching, which was a huge success. And what they did is to define the following energy. So I write it in their notation, but it's very similar to the notation that we saw before. So we have the cost value for assigning pixel P disparity, some disparity that we need to select. And we have the smoothness terms that are defined in this way. So actually, if we have for neighboring pixel P and Q, here they're denoted by I and J. So for neighboring pixels, if their disparity is larger than one, we pay P2, the cost. And for neighboring pixels that their difference of disparity is exactly 1, we pay P1. And if they have the same disparity, we will pay nothing for smoothness as a smoothness term. So that's some simplification that they did. But the more important simplification is that they consider
it's not the same as before, just with a threshold of 1.
It's one way to express psi. Yes, but it's specific choice of psi. Yes. Another contribution is that they consider neighboring only in one direction. That's why it's called semi-global. Before the graph cut, it's called the global matching solution because it considers global smoothness in all directions. Here, they introduced the idea of consider neighboring only in one direction. So for example, here the direction is the upper Y direction. So if that's the direction that we consider, then L and J are neighbors, K and I are neighbors, but I and J are not neighbors, and K, L are not neighbors. So we consider neighboring only in one direction. Another example, if R is this direction, then I and J are neighbors, K and L are neighbors, but in this case, J and L and I and K are not neighbors. Okay, it can be diagonal directions. So in this case, J, K are neighbors, or in this case, I and L are neighbors. So what they also showed that we can go from cost volume that not considering smoothness, where the argmin for each xy over the k disparities will give us a trivial solution or naive solution or winner takes it all solution, which does not consider any smoothness constraint. And they transformed it to a new cost volume that considers smoothness. So in this case, if I'll take the winner takes it all solution, which will be just the argmin for pixel xy over all k disparities, I'll get a solution that considers smoothness in direction R. So that's another contribution for moving from volume that do not consider smoothness to volume that does consider smoothness. And they also suggested a very efficient way to do that. What's the way? So the idea is that this volume can be considered, can be constructed iteratively, row by row. So if I have this direction R, for example, I assume that my only neighbor from row before is already computed. So I know the cost volume for P minus R in this case. I know its volume, its value for each different disparity, for the K disparity. And all I need to know is now compute the cost that considers smoothness for pixel P. So I know pixel P minus R. I know the K values for P minus R. I want to find the value for P with disparity D. So what I need to do is to take the cost, the data term cost, and then I'll just need to add one of the following 4 terms. I can either take the value for D and not pay extra pay because it's the same disparity as I now consider, it's the same D. I can take D minus 1 or D plus 1 and pay P1. Okay, and these values I already know. And I can also take the minimal disparity from pixel P minus R and then pay P2. Okay, so that's my 4 options to get a cost for pixel P with disparity D that considers smoothness in direction R. And since I build it iteratively, I can just fill this volume wherein for each disparity I need to, for each pixel and disparity, I need to go to run K steps because I need to check here K options. But basically, I need to fill n pixels with K disparities. So the complexity is n times K times K. Okay, so it's n K squared complexity.
Can you explain again these questions?
What specific?
How did you get P1, P2?
We defined P1, P2 before. It's just a choice of psi, right?
Okay. And what is the D1 plus 1, D plus 1, D minus 1?
D is disparity. P minus R is my neighbor pixel from a row before that I know all of its cost value. And now I want to consider the cost value for pixel P with disparity D. So I need to get its value considering smoothness in direction R.
Again, D is the disparity value, right? How far is pixel from the current pixel, right?
Yes.
So when you say -1, you say, okay, this pixel is far in 1 pixel?
Yes, compared to the pixel. Now I want to consider pixel B with disparity D. That's the volumetric entry that I want to fill. Okay?
Okay.
Michael.
Yes, it's okay.
When we check for disparity D, we also check the neighbors. So we also look like in the on the previous and one like D plus 1, right?
My neighbor pixel is P minus R, and I want to see to look on its cost for selecting different disparities. Okay, and then build my cost according to my neighbor. But for my neighbor, I already know its cost that consider neighboring. So then I know how to fill my value considering neighboring by taking the minimal value over these 4 options. And I know how much I pay in each option. Okay? It's just a dynamic programming for recursive formula. Okay. Yes, it's a bit confusing, but I think that the idea is great because you look on everything in a volumetric way and you define a new cost volume that considers smoothness in one direction. And then you solve a very complicated cost function without using graph cut. You just use dynamic programming in one direction, which is much faster. And then you get a cost volume that considers smoothness. Now that I get different cost volumes, in this case, I have 8 cost volumes because I considered 8 directions. Okay, so for each direction, I can look at the cost volume and take the winner takes it all solution. Take the argmin D from this volume to get the disparity for pixel XY. And that's what I will get. You see, I'll get 8 different disparity images that consider smoothness in one direction. So you can see, for example, here that it considers smoothness in this direction, but this direction is not smooth. It's very noisy. And here is the opposite thing. And here we consider smoothness in this direction, so this direction is not smooth. So we get what we expected to get. But the nice thing is that I can take the 8 cost volume, sum over them, and then take the winner takes it all solution. And then what I get is a solution that is globally smooth. So using this semi-global block matching approach, I can solve the global block matching. I can approximate global smoothness much faster. So that's the contribution of this algorithm, and it is very popular. It is implemented in OpenCV, and was the best thing to do before deep learning. Okay, so let's see.
Maybe I'm a bit lost. At the end, you're gonna compare it to the previous methods.
Yes, in this slide. But basically, it's much more efficient way to apply smoothness, okay, by considering smoothness in one direction each time.
Because like the difference here, if I understood, is that like we use the same like objective in a sense, right? We compare patches and we we have penalty for discontinuity, right, of neighbors. But here we're just doing it line by line, so it
direction
makes it
by direction.
faster.
We do it direction by direction. We choose one direction and apply smoothness for this direction. So for example, if the direction is the horizontal direction, then the vertical direction is not smooth. Okay, then the reason that you do it for one direction is that you have a very efficient solution with dynamic programming for one direction.
Yeah.
But the one direction is not enough. So, but the nice thing is that you can do it for 8 directions and then get something that is smooth in all directions to approximate.
Oh, so we have like all the 9 directions you showed, right?
Yes.
By dynamic programming, which is kind of fast. Then how can we like aggregate all those?
Yes. So you don't want to average. So you don't want to average the disparity images because it will still look noisy. So the nice thing is that you don't have, before computing these images, you have 8 cost volumes, okay? Where the cost volume itself defines a solution that if you take the argmin, you will get the solution that you saw here. So instead of taking argmin 8 times, you are taking the 8 volumes and average them. And then this volume considers smoothness in all 8 directions together. And then if you take the argmin, you will take the solution that is smooth in all directions.
I'm missing something. I'm not getting it. Like we have the 8 maps we just like calculated.
Mm-hmm. These maps are images, right?
Right.
But before having these maps, you have volumes. What is volume? It's 3-dimensional thing. It's not 2-dimensional. You have a cost for each x, y, and possible depth, possible disparity.
Yeah, a volume is just like the loss value of the pixel, right?
Yes, for pixel and disparity. And this loss value considers smoothness. How you can see that? If you take the argmin from each volume, you get a smooth solution in one direction, right? From these images are resulted from, each one of them is resulted from a cost volume, okay? From volume.
What even like what we see here is a depth map, a disparity map?
Yes, a disparity map resulted from taking the argmin, each pixel, here for example, pixel xy is generated from a cost volume by going over xy values in this volume and choosing d that is the argmin of all these in this volume for this pixel.
Okay. So like we are not seeing the loss values here, right?
Yes,
we store them like somewhere, right?
Yes, I have a volume that stores them, right?
Yeah.
Okay, so but you see the argmin values here. Okay, and that gives you some intuition what this cost volume tries to address, what the problem what the costs are trying to do. Okay, and then if you see what the costs are trying to do, then let's try to average the different costs and then get a solution that is smooth in all directions.
What do you mean by the cost is trying to do something?
I mean that each value from this dynamic programming, I know that for pixel p and disparity d, this is just an entry in this volume. I got a cost that considers smoothness in this direction, in direction R. Okay, so this volume considers smoothness, but in one direction. So if you take the argmin, you will get indeed disparity images that are smooth, but only in one direction.
Each one of those 8 produced by first choosing the direction, which we will enforce continuity.
Yes.
Okay, so now you just per pixel take the disparity that has the lowest loss value.
Yes, in each volume.
Thank
you. You have 8 volumes.
Oh, 8 volumes. Okay, I think I'm good. Thank you.
Yes, I think it's a bit confusing, but I think that if you go over it again, it will be more clear. And the idea is that it's much more efficient. It can.
Yeah, but for 8 inputs, for 8 loss values, we just take the minimal one, and then we take the corresponding disparity, right?
No, you average all the cost volumes. You have 8 cost volumes. Each one considers smoothness in different direction, and you average all of them. And then you take the final solution.
So you average
that's this solution is just for visualization. What the different cost volumes expressing, but you do not use these outputs. This is just a visualization. It's not the final output of the algorithm. It's just a visualization for what the costs learned, because it's hard to visualize this volumetric thing. And then after you average the volumes, then you do what you said. You take the disparity that minimizes the cost, and you get the global solution.
What's the definition of averaging and volume cost? The volume cost is like a tuple, right? It holds the location, right? The XY of the pixel. It's a loss value with respect to the direction we chose. Mm-hmm. And the disparity that we are like a suspect, right? The one that we pick.
Think about
RGB.
How
do you average it? Do you average the X and Y's?
No, you average the value. Think about 2 images in the same size. Okay, you have image of 1000 by 1000 by 1000 with 3 channels, and you have 2 of such images. You can take them and average them, right? Take image 1 plus image 2 divided by 2.
The intensities.
Yes, the intensities. But here the values are costs, not intensities. It's the same thing. Okay.
So what do we get if we just average the cost, the 8 costs? We get an average cost, but like I'm missing.
Okay, so we see
that. Can I try, Yoni? Can I try? If you look on 1 pixel, let you have for each pixel in 2 images, you have 8 channels. Okay, so you do average per element in the channel with different same image from different. So you have the same pixel, and let's say in 1 pixel it's 1, 2, 3, and the second is would be 1, 4, 5. So you do it pairwise, averaging between the 3D depth, and then you get 1 3D box, and then you select for each pixel the minimum of the depth.
No, you take the minimal. You take the depth that minimizes the cost. You take the argmin depth for all possible depths or disparities. But let's not. We need to continue. Maybe we can discuss it later. Okay. Don't want to. There is another small topic that I want to talk about. Okay. So maybe we'll talk about it next. But the idea is that if I take the average cost, this cost considers smoothness in all directions instead of one direction. So I have aggregated cost information for all directions. So here you can see some results that the input image, ground truth, the solution with no smoothness, the solution of the semi-global block matching that we just discussed, and the solution of the global matching methods of graph cut and belief propagation. So that's just a visualization. So regarding deep learning, so we saw that we can learn similarity measure between patches, but then we still need to apply smoothness some way. So for example, Bontar and LeCun just use the semi-global block matching for smooth their assignment with respect, but by using their cost and SGM smoothness. But
before you move to deep learning, what if you have more than 2 images? There are
we'll
some
talk about it next
classic algorithms.
Okay. Yes, next week we'll talk about it. First today we'll talk about 2 views, next week about n views. Okay, so I'll just want to finish the deep learning methods for 2 views this week, and then we'll talk about n views for first classic and deep learning methods next week. Okay. Okay, but there are also papers that try to replace SGM with some learned function, which I don't want to get into this week. And also there are papers that try to improve with deep learning initial estimation of disparity to a better estimation of disparity. But the most recent method and most successful methods are end-to-end. The idea is that you get as an input 2 images and you want to one single neural network to just estimate disparity from the 2 images. But there is a challenge here because there is only limited set of pairs of images with ground truth disparity. It's very hard to tag these ground truth disparities. So it was not a problem for patch similarity learning because each tagged image gives you a lot of patch matches from these tagged disparities. So we can train network from these patches, but for the end-to-end where we need to directly map from images to disparity, if we have only 200 pair of images, then we only have 200 pair for training a network, which is not enough.
What about video games?
Well, great. That's exactly what they did. So they used a video game to synthetically render a lot of synthetic data with ground truth depth, and it's not limited, but it's not exactly look like an image of a road from a car. So it's not good enough for the final estimation, but it's good to initialize a network with computer games, with computer graphics, and then finally they use the 200 images to refine the network to the specific domain, and it worked very, very nice. So one of these methods is called GCNet, which published 4 years ago. And the idea is to build a cost volume and use a neural network to handle the cost volume. And this was the first end-to-end method to be ranked first at the benchmarks of Kitty. But today they are ranked 88 and 186, according to 2 days ago. Maybe it's changed already, but it's changed very fast. There are a lot of published methods in this domain. And let's go very briefly on what they suggested. The network gets 2 images. It uses a 2D convolution to extract features from the images. So for each pixel, I have a feature vector. Then I build the cost volume. According to disparities, I know which pixels to match. So I have a volume of size D, which what we called K before, the number of disparities, height and the width of the image. And for each disparity, I have 2F. I have 2 features that I try to, of the 2 pixels that I try to find correspondence according to see if they correspond according to the disparity. So it's just the cost volume without the metric, just put the features in this cost volume. but it's a three-dimensional image, D by H by W, with the information from the features of the images that needs to be used for finding cost. So then what they did is used 3D convolutions that try to apply smoothness and semantic constraints also, which before we did not know how to apply, we just applied smoothness. So they can learn how to apply these constraints, these global constraints. So the first convolution used local appearance information for and with some global context from the image, and now we have global smoothness information that is applied, and in the end, like in the SGM, we expect to have a cost volume that considered smoothness, and then we take the winner takes it all or the soft argmin to make it differentiable and to get a disparity. So that's what their solution. And here you can see some results. That's the input image. That's the result of the semi-global block matching in OpenCV. It's a bit noisy. That's the solution of the network that was learned to find patch similarity, but still with SGM, with semi-global block matching. So you see that the result is better.
The outliers here is comparing to some ground truth that we hold.
Yes, there is ground truth, and it's not specific to this image, it's average of the entire test images.
Is there any methods that take as an input also the segmentation map generated from other model or so?
I think that there is something, and yes, there is a paper. I can search for it, but I did not put it here. Yes, but you can use. There are also a lot of papers that use a sparse depth information. For example, usually with cars you have LiDAR sometimes for autonomous cars, and you want to get the dense disparity. So you have stereo cameras and you have LiDAR, and you want to complete the depth. But let's not, there are more stereo methods, but here I considered only method that gets two images and outputs disparity.
But okay. You just like mentioned it, and this is also looks like a road, and like vehicle and stuff. So the things we talked about, they still hold when we have like moving objects like cars?
No, so it's not. You need to have no movement. So basically, this method can maybe learn how to ignore moving objects, but it's a problem. And there are also methods that try to segment out the moving object. So the assumption is that the scene is static.
So this is no, we cannot apply any of it in like
yes, but think about if I have stereo cameras, then and I take the image at the exact same time, then from my point of view, the scene is static, right? It's not like I take one image, moved, and take another one, and things could move. I take the two images in the exact same time. I have two cameras on the car. So everything is static in this case.
Yanni, what happens if I don't have a stereo images? I have two images, but they are not stereo.
Okay, so we will see next if we have time, or we discuss it next week. Okay, so that's the best solution for now. It's ranked 3rd and 4th in Kitty. So its total ranking is the best according to what I saw. And you can see it compared to the ground truth.
What is Kitty?
Kitty is a benchmark of that compares methods. They don't give you the test images, they give you just training images, and they you can upload your code to their benchmark to evaluate your method. So it's a way to rank different methods. Okay, so you see that the results got better over time, but there are still challenges. Here, the outliers, there are still 1% of outliers, and you can see sometimes over smooth, like here it connects the pole and the tree. See, it's still not a solved problem. Okay.
But it is 6 years ago, right?
What, 6 years?
This
yes, and Kitty is 9 years. Kitty 2012 is 9 years.
No, this model, the sterile, how old is it?
It's very old. I think the first solution was suggested about 30 years ago, but it's a problem that was interesting even before you, ever since you had cameras. You wanted to see if you can use your cameras as a measuring system to measure depth, like your eyes do. Like your eyes do, your eyes are actually can sense 3D information. So ever since you could have cameras, this problem was interesting, if you can use it to measure depth. Maybe we'll talk about it briefly because we have 5 minutes. And so, okay. But remember, until now, we talked about rectified images. But in general, cameras are not rectified. And the idea of, we don't have the simplified rectified stereo pair. So the idea of the rectification phase is to use homographies to change the images such that they are rectified, which means that you see here that lines that are parallel to the x-axis are not epipolar lines. They're not matching pixels, but in this case, there are. And the rectification process is to make images rectified even though they are not. So for this, we do the following steps. It's relatively simple, so let's go over it briefly. First, in images, this point is usually 0, 0. We first want to map it to the center of the image. So we reduce the center from the coordinates, and we get that the center of the image is 0, 0. Then we rotate the image such that the epipole has a 0 y coordinate. Okay, you can always find this. It's very simple. Next, now that we have that it has 0 height, we can use this G, which basically keep alpha and 0 in the second coordinate, but change the third coordinate to be 0. Okay, by just multiplying, applying this transformation G on the image. So what it did, it maps the epipole point to infinity in the direction of the x-axis. So basically what it did, it make all the epipolar lines parallel to the x-axis. So to sum up step 1, we have 3 steps. We first move the center of the image to be at 0, 0. We rotate the image to have epipole with a 0 y value, and then we map the epipole to infinity to get parallel epipolar lines. So we can concatenate this 3 transformation and get the homography H1 that we apply on image 1. But what about image 2? It can be shown that if we know H1, H2 can also be known as HA multiplied by H0, where H0 is known matrix, decomposed to H1 multiplied by M, where M is known from the fundamental matrix. And HA is any hyphen transformation of this form. So I can, for example, use identity. I can choose A to be 1, B0, C0, and then HA is an identity matrix. But it's better to choose HA that minimizes distortion, because I don't want my rectified images to look very different. So what we do is we take set of sparse correspondences, xi and x bar, and we try to find age a, which is the only unknown factor here for now, such that it will minimize the distance between xi and xi bar after the rectification. And this can be solved linearly. And here you can see some results. That's the input images. Epipolar lines originally are not parallel to the x-axis, but after rectification, and here line parallel to the x-axis are not epipolar lines, but after rectification, you see that it is the case. You see that lines parallel to the x-axis are corresponding epipolar lines. Everything is matched here between the corresponding epipolar lines, and you can see the two rectified images where corresponding points are just in different disparities. Okay, so then we can, once we have the case that we only need to compute disparities, then we can use disparity estimation method. Here I used the semi-global block matching disparity estimation, and I got the following results, which give me dense correspondences, and then I can just reconstruct a dense structure of the scene up to occlusions between the two images where I don't have matches. So let's skip it. It just shows some limitation, and there is method that can solve the cases that the epipole is inside the image, and we don't want to map image point to infinity. And also, so the limitation here is that we cannot reconstruct occluded point, and that's why we want to use more images if we have, and that's what we will talk about next week. So to sum up, we talked about stereo cameras, disparity and depth. We talked about dense matching and regularization and smoothness, where we discussed the alpha expansion algorithm that used global smoothness, semi-global block matching, which is much more practical. We talked about deep learning approaches for disparity estimation, about the MCCNN that learned patch similarity, and about end-to-end approaches that improved disparity estimation a lot, and about how to rectify general images to be used for disparity estimation. And again, to put this in the context of the course, because I asked several people and they said that they lost the big image. So before today, we talked about sparse point matches and sparse reconstruction for two views, and today we showed how to get it for how for two views we can get a dense reconstruction. And before today, we talked about structure for motion that give us for unordered images, sparse reconstruction and cameras. But next week, we will talk about how to get dense reconstruction from multiple images using known cameras. Okay, so sorry for 2 minutes late, but if you have more questions, feel free to ask.
Yeah, I have a question. We use the disparity when we reconstruct the 3D scene, like a matching point. We want to just, this disparity will give us every point to match another point, right?
Yes. Yes. Because if you have a match between pixels, then you know the cameras, then you can triangulate the match, right? We know how to triangulate point. The reason that this reconstruction is not dense is because you don't have matches. If you have matches, you can get dense reconstruction.
But it means that we also need to have two images that are just with like two cameras and images, of course, with only translation between them, right?
No, that's what we showed in the rectification.
But here, yeah, but here with the rectification, so you get like some of distortion when you use the homography, right?
Yes, I agree that for if you are using rectification, you distort your image a little bit. Exactly. Yes, you have to distort the image in order to rectify images and use stereo algorithms.
Is it something that like you would choose to use when you have like images of I don't know, Rome and things we saw in previous lectures that are like they are not so flat, you know, and you have images and cameras from different locations and orientations and stuff.
So for the multiple views, we will talk about a bit next week. You usually use a different way. You don't rectify every pair. You use what it called plane sweep. But in this, if you use two cameras, you need that there will not be with too large baselines. So you will be able to find correspondence sets without too much distortion. Another case that can result in high distortion is if the epipole is close to the image, as you see here. Then you apply a big distortion to the image, and then you might want to use this polar rectification algorithm by Polyfice et al. But in general, it works very well. I mean, I did not do anything special here. Just use the images and extract cameras and rectify them in SGBM, which is not state of the art, give us a very nice result. There are still some missing parts here and some errors, but we get much denser construction than before. Like that's what we had before and that's what we have now. So we got much denser construction.